So if you go to China,
So
go to China, probably cost you like 20 cents in American
These were
dollars.
like $12.
American.
Wow, you splurge.
Wow.
I know.
That's like high end in China.
Alright.
It is. I'm really making that up. $5 are made of a lot of kinds. It is.
Really? I think how many kids they have there. They're not very good at this.
Huh? 0, but I know the conversion rate. In our dollars is a lot.
I mean, the dollars are the same.
To yuan.
In China.
What to?
Yeah, pretty sure.
Or pesos.
Alright, so this lab is about weldability of steels. Or basically, like weld defects that you commonly see in steel. So what are, do you guys remember some of the cracks that you will see in steel? HIC? Good. What else? Lamellar cracking?
Preheat.
You can't, wait, what'd you say?
Preheat.
Reheat, oh, reheat cracking. I think I said preheat.
Some ductility, Deb.
Alright, okay. Okay, so this first sample you've seen already in lab 3. This is hydrogen-induced cracking. You guys remember? Look familiar? Alright, but this is a CTS test, and it's not a group. The group isn't machined in there. That's actually a second test. I think I told you guys that in lab 3. So, that's not bad. But the CTS test is basically you take a square block and you weld it on top of a plate, and then you weld the two sides, wait for it to cool, and then weld the other two sides. And then the restraint will
The
cause.
restraint is present because of your first 2 welds.
Yeah.
Right there?
Sure.
Alright, so describe that test. Alright, so since we know this is a hydrogen-induced cracking, where do you see the crack localized at? Can you
The stress concentration.
What do you want?
Yeah, the fusion. Alright, so there's a stress concentrator, right? Where in the, relative to the weld, where's the crack located?
Along the HAZ.
Along the HAZ, right. Which part of the heat the coarse grain heat affected zone, and why is that? The martensite. Right. So there's susceptible microstructure there due to the martensite, and it starts at the stress concentrator, so that's where your restraint is the highest in the weld. Okay? Is hydrogen-induced cracking transgranular or intergranular? It's both. Good. There's a graph that Antonio drew back there, and basically it's saying that at high stress and very high hydrogen levels, you're going to get microvoid coalescence, which is a transgranular type of cracking. And then as you get less strain in your sample or less hydrogen, you're going to have it's going to be more intergranular. So when the crack starts, it's more likely to start transgranular, or if there's not that much strain, it'll just be intergranular. But as it goes on, it's probably not going to go from intergranular to transgranular. It'll be transgranular to intergranular. Does that make sense? Because when you start cracking, you'll relieve some of the stress that's in your part. Right? Okay, so what does this crack look like? Inter or transgranular?
Starts out transgranular.
So,
Let's go.
alright. So what does that look like to you guys?
What?
Transgranular.
Great answer.
Does it look transgranular? I don't think it looks
I don't think so.
Intro.
So if you like go up. So how can we tell if it's transgranular or intergranular? What are some of the ways we can differentiate between them?
What do you think a transgranular flag looks like?
It's going to be very significant, like boundaries, curving around boundaries.
Right. So it's straight. Someone said that it's pretty straight. You won't see like the jagged edge that where it goes around the grain boundaries, right? And another way you can tell is if they're bigger grains, the two sides of the crack will have the same orientation if it's transgranular, and different if it's intergranular. Does that make sense?
Can you repeat the last part you just said?
So if it's intergranular, the two sides of your crack will have different orientations, right? For the packet of grains or
So this is like most likely intergranular.
yeah, so this is pretty much all intergranular. There might be some transgranular in
At the
there.
bottom of the screen, a little bit. Look a little bit, but look, secondary crack.
Yeah, like maybe the secondary.
Right there. The secondary crack.
That one. Okay. What else? Oh, what does the microstructure look like here? I think we already talked about that. Yeah, it's one side. Good. Does hydrogen-induced cracking, where can it happen in the weld? Anywhere. Right.
Usually happen in the affected zones.
Yes, usually in the coarse grain heat affected zone, that's usually where you'll see all of the martensite, the cooling ring, and stuff like that, and also the strain. What are the things that you need for hydrogen-induced cracking?
Hydrogen temperature, source of hydrogen,
Yep, hydrogen, temperature,
tensile stress,
restraint,
susceptible
and susceptible microstructure. Good. Y'all pretty much understand this. Oh, can you go to? There's also a straight.
Oh, okay.
Alright, so this is pretty.
Come on.
Alright, so do you guys see that straight region right there? What do you think that is?
He definitely said it. What?
Well, it's not. Okay, so not it's a specific type of crack. So, okay, so what do you notice about the base metal? Here.
on the roll.
It's rolled. It's a rolled part. And what do you see
What do you think, Carrie?
in...
So the crack is like following like this kind of the string of lines.
Yeah.
Alright, so Jerry said that this crack is kind of following that string. Right, lamellar cracking. Do you guys remember? Lamellar cracking occurs usually in rolled materials, and then this, that line that you see that it kind of follows, there might be a stringer either from impurities or intermetallics that are forming there that causes very low ductility in the short transverse direction. So any questions? So basically, talk about hydrogen cracking, why it happens, where you see the crack in the weld, describe,
How do you know it's
crack.
hydrogen cracking?
yeah, so like inter or transgranular.
Give me a paragraph or two about the test. Please put that with the sample. Got it. Any questions? Put on.
Alright, does anyone remember what the implant test is? No one? No.
Gary?
Is it a toughness test?
No. Alright, so the implant test is it's usually for hydrogen-induced cracking. So what'll happen is you drill a hole in your base plate to the bottom of where your weld's going to be, and then you lay down a weld. Is this the lowest thing?
No, definitely not.
And then you lay down a weld at the top of that threaded screw where it meets the weld. And what you do is you put a load, you screw on a load that pulls down. It's a constant load on the weld, and if it cracks, this one obviously didn't crack.
So this one didn't crack, so concept, here's your where it got welded. This is like your screw you put
That's the
in.
heat affected zone up there.
This is like where you attach it to pull your load.
Does that make sense?
Hold the load like while you're welding or right after?
It's after you're done welding. Yeah. So when does hydrogen-induced cracking occur?
24 hours.
Right, so it's after. So this test would, I'm pretty sure it's run after it's like cooled and stuff like that. So it's a constant load. Pretty much you're just trying to figure out how long it takes until it cracks.
What microstructure is present in the coarse grain heat affected zone? Good. So for this sample, you'll basically do a comparison for A to B. Same test was done, different materials, different loads. So
And then,
do some comparison and say why one failed, the next one did fail at a lower load. So
and the threads are usually, those are usually stress concentrators that are what's effectively the base material.
So is that what the thread part of the actual screw that you screw in there?
Yeah.
Is this the red with the buckets in the label room?
That's DHC.
Never mind.
Why do the threads look like it's only half the screw?
because you're looking at a cutout.
Yeah, so this is a cross section.
So cut a screw in half, and that's what you'll see. Got it?
So this would go all the way around.
See how the
Right.
points aren't the same height that it's wrapping.
Oh, okay.
Good.
Does that make sense?
So it's not threaded into the plate.
No.
No, it just has threads, and you just put it in the
Yeah.
hole, and that's what you're welding.
Yeah, so you're drilling a hole into your base plate, and then the thread is going, and then the threaded screw is going to the bottom where
Yes.
you're welding it.
The threads are so you can pull it from the other side, right?
Yeah.
So is it like the screw like hollowed out in the middle?
No. You can see the middle right there.
So it's like a hole, and then they stick the screw into it, and then they
Base
weld
plate,
the
hole,
screw over it.
put the screw in, screw sticks out, you weld the screw, wait for it to cool, hook on, your load's pulling it out. If it holds, that's fantastic. But as you'll see in the next sample, it does not hold. If
So
we're
what
ready?
should we take pictures of for this one?
Both.
Oh, what
So
you-
coarse grain heat affected zone, fusion line area, say why it didn't fail, what microstructure is present.
Yeah, so
Okay, you'll do a comparison to the one that failed. People in the front, you can see it. There's a big gap. So, all right.
That was sample A.
yep,
That was sample
so
A.
that one is the HSLA, which means what?
High strength, low alloy.
High strength, low alloy. Okay, good. So the next one is pulled under a lower load. So what does that tell you maybe is the cause of the failure? Or like what the difference is? Sorry?
It's a lot weaker.
It's a lot weaker.
That's good.
Right. So what do you think would cause that? If you're comparing HSLA 100 to HY 100. What do you think you're going to have to look up and put in your lab reports? Carbon content, composition, stuff like that.
Alloy elements.
So this tests the material that the screw is made out of?
Yes.
Okay.
Not the base number.
But typically, like a lot of times they'll use the same base material. That.
And filler metal? Or-
No, they'll use the screw is usually the same material as your base material. Because
Oh,
that's
okay.
usually what you're testing.
What does this test mostly measure?
Oh,
What do you mean?
Like, what is, like, is it hardness or like
Oh, when you
Hydrogen
when you
induced
Google it,
Oh, that's it?
It's
For this test?
Yeah.
Oh, like,
Google it, read the book. Again, you'll have to write a paragraph or two about the test, put a test for it, stuff like that. Put it with the samples. Only write that once. Just like start out and then go sample A, sample B. Got it? Good. So, I see a failure here.
What region relative to the weld did this fail?
Coarse grain.
Right. Okay, good. Do you see any microstructure indicators?
Martin's like
Martensite, good. Intergranular or transgranular?
Who said trans? Who? Where do you see it?
If you go to the right,
Like
isn't it that step right there where it's really straight?
That one?
Yeah. Right next to the.
Might be the edge of like
I think
the 3 grains.
Okay.
Yeah.
There. Yeah, it's kind of hard to see in this one because you don't have the other side.
Huh? You want me to go all the way to the right?
Yeah,
Jerry
like
thinks he
towards
got it
the
now.
top. Like right there.
well,
That's pretty straight.
Well, maybe.
That might be. Yeah. Again, it's kind of hard to tell on this one. You can't really.
But on this key.
So when it's
Or could
when
it
it's hard to
start
tell,
to
you kind of base it on how jagged it is.
Usually.
So does anyone
So, like-
see transgranular now?
Yeah. So
Use
like
the
here, you
mouse.
can pretty confidently tell that it's intergranular
You think
and not
so?
transgranular, right?
Yeah, a little square.
Oh yeah, like
Oh yeah. It's pretty much, put this in your lab report as your
So
transgranular.
he was saying that this one looks transgranular, I think.
How can you tell other than being straight?
it's like cutting right through the last.
So slap them together. The crack wasn't there. They should almost line up.
Sorry.
Anything else? Anybody?
Are you talking about the little?
Right next to the mouse.
Yeah.
I can zoom in one more.
We can find that exact spot.
The sample is not that big.
You want to just take a picture for us?
No. I will not.
Send it to the group picture.
Any questions on these two samples? So this one and then the one we just did.
Yeah,
pretty straightforward.
everybody see it now?
You're comparing the two in terms of what happened, what kind of cracking.
Huh?
It's like a hamster wheel.
Sounds like more than
Sounds like a hamster wheel.
Alright, no questions?
Everybody good with the sample? What you're supposed to do?
Yeah.
Good.
Where is?
Where's what?
Where
I
is
was gonna
what?
say where is that like relative to the?
It's very
Like,
easy
take
to
those
find.
in.
There's not much to look for, so or you just need to go left and right, and you'll find it.
Alright, so the next one.
We'll do the mystery steal.
Next one is the mystery seal. So the fillet weld. You don't know where the steel is coming from. You don't know what process, like the history, processing history. But you're going to characterize the cracking and speculate to the mechanism of what's happening. Michael? Alright, so this is the fillet weld. This is one of the sides. Alright, so where's the crack located? Just concentrated.
Coarse grain.
Coarse grain heat effect of the. Okay, good.
It's full crack.
Alright.
Okay, so it's just concentrated. We'll start.
And then let's look at what else should we look at for this crack to figure out what it is? Microstructure. Good. Alright, so what does it look like? Martensite.
What type of cracking do we see? Inter.
Intergranular. Good. So what do we think it is? Hydrogen-induced cracking. Good. What else?
All these are very.
Yeah, pretty much. So it's mostly intergranular, but there is a spot that it might be transgranular over on the other side.
That looks pretty straight.
Yeah, like on the bottom.
Right there.
So since it like ended there, it probably propagated from the other side.
From the other side, yeah. So if we go to the beginning of the one, so that might be intergranular right there. Right there. And then if you go to the beginning of it.
See how it looks less straight, more jagged edges. Tipper. Yes, no.
Yes.
You can say no.
Amen.
Okay. Everyone get how you can prove it's hydrogen-induced cracking there?
Yeah. And over here it might be some transgranular, right? When it starts, it's going to have a high level of restraint. And then your hydrogen will typically gather at the stress concentrator.
Did it shear that far apart, or is that like machined in there?
I think it's sheared that far apart.
No, that's,
Oh, this?
yeah, that's
this is
just where the
machine.
fillet weld doesn't reach.
Yeah.
Because that's kind of the gap between your
The two plates.
T-joint.
Gotcha.
Oh, so
Everyone got it?
Is it welded with the same material as the base metal?
We don't know. Why it's the mystery
Probably,
steel.
probably not.
We don't even get a hardness then?
No.
Oh.
Wait, so we just need
I'm gonna do
say
myself.
what kind of crack it is.
You describe the cracking, what kind of cracking mechanism it could be, and why you think that. Basically. Yeah.
We got it?
We can basically assume it's fine, so we don't have to prove it was fine.
Yeah, it's
You're
pretty,
right on the
pretty
course cracking
clearly
affected
marked.
zone. You know it's a steel. Pretty much know what it is. That's good. That looks like martensite
It
to me.
looks pretty clearly martensite.
If you're a 6 lab, if you're educated enough, you can identify martensite. I feel confident. Pretty good.
Any questions? Alright, this one has gone through a reheat cracking test. Does anyone know what that is? Or how it's done? It incorporates reheating, yes.
Thank you for the obvious answer. You're welcome.
Alright, so this one is actually run in the glue ball. I think it should be described in the book as well as your lecture slide, so put some information on that. Right? Reheat cracking. Reheat test. So this one is T24 steel sample. You might have to look up the composition, but there's chrome and moly in it. So can anyone describe the mechanism for reheat cracking?
Okay.
So,
No.
oh yeah.
Good answer the whole time.
Precipitation or reprecipitation of precipitates inside the grain, and then there's a region that's precipitate free right next to the grain boundary.
Yep. Right, and then what else happens? There's something else you need other than precipitates.
Restraint.
Restraint. Good. So basically, when this is undergoing the post-weld heat treat or any type of reheat, the residual stresses of the weld are decreasing, and then your precipitates are forming on the inside of your grains, and also right along the grain boundaries. So next to the grain boundary, there's that precipitate-free zone, right? And then your stresses are going to be concentrated right along that precipitate-free zone, and that's where you get cracking. Any questions?
So the one thing we didn't go over was, so these are like your smaller cracks. Here's where it actually.
Yeah, so this is the failure, that's the reheat crack failure, and then you can see the reheat cracking happening right here along the grain boundaries. There, here, there.
Pretty good.
Got that? So,
Talk about the test done.
does anyone know what elements or precipitates usually occurs in steels?
Take a guess.
No. Titanium and aluminum is for nickel-based alloys. So that's yeah. So it's the chrome moly and vanadium. And this is actually a chrome moly steel, but you'll still have to probably look up the composition for that. Right? Does that make sense? Does everyone hear that?
Oh yeah, I hear it.
And what are these dark spots that are here on this? No, they're not precipitates.
Here where the mouse is.
That's from the
No,
actual.
that looks like an impurity to me.
That's
That
the
one.
engine.
Kidding. Definitely from the engine. Okay.
So don't label that as precipitate.
So,
Well, what's the microstructure here? What does it look like?
what are we thinking? What? No. Who else? We'll eventually run out of options. So.
Fairlight.
No.
Martensite.
No.
Yeah.
No.
Austenite.
That's 110 wrong. Okay. We're left with one.
Martin's.
Separate.
There we go. It was reheated, guys. Come on, that should have been a giveaway.
Alright, so separate martensite.
If you reheat something, I mean, what are you bound to happen?
And the precipitates are pretty small, so that's why we can't do them.
Anything
You
else?
zoom in a lot because you see the.
Not here.
Not in the obstacle.
But yes, there are ways to where you can see the precipitate free zone.
You guys know what edge this one was?
Do you do a song about
Really nice off.
Alright, any questions
Really, you don't think so?
on the sample? Yeah, we're pretty much done though. So.
Now it's just kind of us talking for a minute or two.
Alright, any questions on the samples, on the cracking? Alright, so for the last part, you're pretty much just doing like hydrogen cracking standards.
Everyone learned how to do this yesterday, correct?
Right. Well, on the carbon page, there's a kind of like a slideshow tutorial thing that tells you how to do each part of it
For this
So make-
class or that class?
for the lab class. So make sure you show your work. Even if you're not the one assigned to this problem, you might want to know how to do this problem.
Could be on your exam next week.
On
I'd more
your
say it's
final.
going to be on the final. You just learned this. This is not easy.
I mean,
It
yeah.
takes practice.
It's-
So if you don't practice it, you're not going to know what you're doing.
It's not necessarily hard, but
It's
you
not
do.
hard, but if you don't practice it and do it,
Yeah.
you don't know what you're doing. You'll get it wrong. So everyone, you got to do both types of methods. Each person in the group, take one, knock them out. There you go. Or take two and then compare answers with each other to make sure you did it right. So best way to learn.
Any questions?
That's it.
That was extremely visual.
Thanks.
Yep.
When he said, like,
Did I get that? Not just parrot.
you ready to reheat tomorrow?
Yeah.